This is lesson number 2 in the Ethernet IP core. In this tutorial, we'll be talking about the MII model, Media Independent Interface. So this model is responsible for sending and receiving control data between the two sending and receiving device. The data it sends is different from the main data that is being transmitted between the receiver and the receiving station and the transmitting station. This data is the control data. So what exactly are these control data? These control data are configuration data that are used during the transmission. That is, this data includes whether there should be preamble settings to know if there should be preamble to be sent, what form of CLC error checking are they using, what is the size of the data, is it the CLC, is it 7 bits or 7 bytes of data, the preamble, what configuration is it, are they all ones, are they all zeros and one. So the receiving station and the transmitting station have to exchange this data before sending and reception of data. So this helps them to know what they're expecting and set their configurations on time. So this model has other 4 sub-circuits which we'll be treating individually. It has the clock gen. This clock gen is responsible for generating the clock. These models separately, individually. So let's start with the first one, which is the clock gen model. As now, this clock gen model, this is what it looks like. This model generates the MDC clock. This is the MDC clock here. This is the main clock used for the MII model, the Media Independent Interface model. And to the frequency of this MII model is dependent on this divider input. This input comes from the register. So whatever frequency you want to get, you have to set it from the register to set this divider input from the register. So here is a comparator. This comparator makes sure that this divider input is greater than 2. That is, in a situation whereby is less than 2, this is a comparator. If it's less than 2, this is the value 2. If it compares this divider input with the value 2. If it is less than 2, whereby the divider is less than 2. But if it's greater than 2, then if it's greater than 2, the divider takes back its original value. That is, if it's greater than 2, the divider goes in here. If it's less than 2, it takes the value 2. Then here, At this point there is a shift by 1, a right shift by 1, and we know that in verilog shifting by 1 means division. So this divider input comes from the register module. So when it comes here, it's being compared with this value of 2. Now we have a comparator here. This is a comparator. It compares this divider value with the value 2. If the value is less than 2, it automatically turns on this multiplexer here and assigns the value 2 to it. But if it's greater than 2, it takes back this original value that is in the divider. So why does it do this? Because at this point the clock divider will still have to be divided by 2. So here is the shift right by 1, and shifting bit by 1 means dividing it by 2. So when this bit is being shifted by 1, it means it has been divided by 2, and dividing a value that is less than 2 by 2 won't give you a real number. So that is essence of this comparison, comparing the divider with the value 2. So once you've been able to shift it by 2, the new value is now being fed to this multiplexer. So here we have a RAM. I call it RAM 8. So what is basically this RAM 8? I use a lot of this RAM in this. RAM 8 is just a combination of 8 flip-flops. This is it. It consists of just 8 flip-flops. So this 8-bit RAM is being latched here. It's being latched here. So whenever you clock this circuit, so this comparator here compares the value in this RAM with 0. So whenever the value in this RAM is equal to 0, a high signal is sent to this multiplexer, and once this multiplexer turns on, it takes back the value of the divider value, that is the one coming from this divider, goes back into this RAM. When it's not 0, it takes back this value here. This is a subtractor, so it's more like a countdown timer that keeps decrementing the value in this 8-bit RAM. The value keeps decrementing. Whenever it's 0, this comes on. Whenever it's 0, it comes on and takes back the value in this divider, the divider value, and the cycles continues that way. In this way, that is how this new clock is being generated. So that is how the new clock is being generated. So what does this do? Whenever it comes on, so for every time it gets down to 0, this multiplexer keeps switching between 0 and 1, 0 and 1, thereby generating the clock. This is the opposite, the negative of what it has. So it's more like switching between 0 and 1, 0 and 1. So this divider determines how long it takes for this clock to change, therefore generating the new clocking frequency. So these two new clocks here, one gets the positive edge of this MDC clock, and the other one gets the negative edge of this MDC clock. So at the end we have, so it assumes we have 3 outputs, the MDC, this and this, but this MDC is the main clock for the whole circuit. I'm going to show you where we use these other 2 clocks. So one goes high at the positive edge, that is whenever it goes down to 0 and this one is on, this comes on, and then whenever it gets down to 0 and is off, this one comes on. So these two other extra clock, what they do basically is they determine the positive edge and negative edge of this MDC clock. So that is basically what they do. So I'll demonstrate the working of this MDC clock to you. So as you can see, this comes on whenever this is on and this is 0. So it detects the positive edge, the rising edge of MDC clock, while this determines the falling edge of this MDC clock. So, and as you can see, assuming this divider, let me make this divider 0. So this multiplexer automatically comes on and sets the value to 2. So but if I make it higher than 2, let me use a high value, it goes off, and then we are now using the normal value of the divider. So it sends the input down here, and whenever the value in this RAM is 0, this multiplexer comes on and takes back the value of the divider into the RAM, and then this subtractor keeps decrementing it for every clock cycle, and this comparator makes sure whenever it's 0, it turns this multiplexer on, and it keeps pulsing, switching on and off, thereby generating this MDC clock. So these ones are the rising edge and the falling edge. So in the next tutorial, I'm going to show you how we use this other remaining 3 clocks. So note that the divider comes from the register module. That is where all the configuration settings of the Ethernet core is being stored. All the configuration settings are stored here. You can determine what frequency do you want. Then from calculation, you can change this divider value. You get a different frequency altogether. So next tutorial will be demonstrating how this other 2 clock works. The MDC clock will be used to clock the two transmitting stations, the receiving and the transmitting stations, for exchange of controlled data, not the main Ethernet frame. At this point, it's just the control data frame that is being sent using the MII module. So you find the code for this clock gen on the website. This is the code for the clock generator on the site projectfpga.com/tcp.